Hi, I'm going to talk about database reconstruction from noisy volume, which is a cache side channel attack on SQLite. So this is a joint work with Mahammad Shirinov and my advisor, Dachman-Soled. So the model that we are interested in this work assume that we have multiple user. Each user has access to his own database. So for example, user 1 has access to database 1 and user 2 has access to database 2, and the server is trusted. So what happens if one of the user act maliciously? So we are going to show that the attacker in this case, by just interacting with the trusted server, can gain some information about the database that he doesn't have access to. So let's remind you about the cache attack. So look at the figure on the left-hand side. So we have a victim and attacker, and they shared some hardware. And also they share the same library, which is a SQL. So once the victim issue a query to a SQL, he will get a response, and the attacker, as a result of side channel, will get the know that one row was returned to the victim. So what will happen? So for example, look at the figure on the right-hand side. The victim asks for a range query on the column grade and for the values between 1 and 1. And as a result, he'll get a row A. And also if the victim issue a new query, he will get a new response and the attacker will see that. So basically what the attacker will see is that the volume of the response from the SQLite. So he can recover the volume of the responses. So let's see how the attacker can do that. So the attacker basically run a flush and reload using Mastic toolkit. You can see a simple trace here. If you look more closely, we can see that the attacker monitored 2 lines, and by just counting the cache activity, he can recover the approximate of the approximation of the volume. So here's how the attack works. The attacker will continue gathering traces for each query. He will aggregate the information he obtained for each trace, and as a result, he will get a figure similar to the one shown on the right-hand side. So the red dotted lines are the correct volumes, and the blue lines are the volumes recovered by the attacker. And as you can see, the attacker recovered an approximation of the correct volume. So the value that the attacker recovered are quite close to the correct one, but they're not exactly equal. So here is a good place to look at some of the related work. So the 2 works of Claris et al. And Grubbs et al. Assume a malicious server. Claris et al. Showed a database recovery by observing volumes, but they made an assumption that the range queries are issued uniformly. Grubbs et al. Also showed a database recovery attack using a clique-finding algorithm. They assume that each volume is observed once. Our contribution is, however, focused on a weaker adversarial model. In our case, the server is trusted, but some side channel information is given to the attacker. So the attacker can recover the volume of the responses using the side channel. Since the volumes are coming from the side channel, they're inherently more noisy, and also we might be missing some of the volumes, and we will show that we can recover some database even in these cases. So let's remind you about how the previous work used the clique to recover the database. So the database that we are interested in is on the right-hand side. I listed all the volumes from running the range query on this database, and the volumes are 1, 4, 2, 5, 2, 5, 6, 7, and they're shown in the figure in the middle. The figure on the left-hand side, however, shows all the range queries, and we connect two ranges together if there exists another range such that the addition of the 2 will give us a third. So for example, the range 1, 1 and 2, 2 will give us 1, 2. So we connect 1, 2 to 1, 1, and so on. And if you look at the figure on the middle, we connect 1 and 5 because there exists a 4. So there is a connection from 1 to 5. If you look at the figure on the left-hand side, you can see that if we recover, there is a clique of size 3. So why exactly 3? It's because the ranges of the grades on the database on the right-hand side is up to 3. So there is a clique of size 3. So it's 1, 1, 1, 2, 1, 3. And moreover, you can see that from subtracting 1, 2 and 1, 1, we'll get 2, 2. And also from subtracting 1, 3 and 1, 2, we'll get 3, 3. So that's what we call a database reconstruction using a clique. So if we connect all the possible ranges using that, you can see that we get the figure on the middle. And you can see that there are multiple cliques there. And one of them will give us 1, 4, 2. And also the mirror of that, which is 2, 4, 1. And this is the actual data. This is the actual recovered database. And you can see that on the figure on the right-hand side, there exists 1 element with value equal to 1, 4 element with value equal to 2, and 2 element with value equal to 3. So let's move on to the case where the measurements are from the cache. So this is harder. I mean, by harder means that some of the volumes might be missing, some of the connection in the graph is missing, there might be some extra volumes in the graph, and also there might be some extra node in the graph which should not be there. And as a result of that, the clique might not form properly. So what we show here is we show 2 contributions. We show that we can change the way we connect nodes, and also we extend the clique-finding algorithm to recover even more databases. So look at the figure on the middle. So in this case, since the nodes are noisy, the values of each node is approximate. So they're not exactly equal to what is there. It's approximately equal to what is there. So what we do here is since the values are approximate, we might be missing some of the edges, and the clique might not form properly. So what we do here is we change the way we connect nodes. So for example, we connect A to B in the case that B plus C is approximately equal to A. And the approximation is determined by noise parameter, which can be recovered in a pre-processing step, which involves mounting the attack on a known database. And also you can think of it as an offline phase of the attack. So how we extend the clique-finding algorithm? So look at the database on the right-hand side. So it has it has a range 5. So we are basically looking for a clique of size 5. The figure on the left-hand side shows the case where the volumes are perfect. So the clique of size 5 forms. But the figure on the right-hand side, however, the volumes are noisy. And even though we change the way we connect the nodes, we might still be missing some of the edges. And as a result of that, the clique of size 5 might not form. So what we'll get is actually a clique of size 4. So you can see here that we have 2 clique of size 4. From the first clique, we recover a database equal to 29, 99, 81, and 30. We call it base solution, and we are trying to extend this base solution to recover the actual database. So from the second clique, we recover the database of 29, 180, 30, and 60. And you can see that the second and third element in the first database is equal to the second element in the second database. That's what we call the match phase of our algorithm. And also, we can extend an extra element from the second solution. So we get some approximation of the actual database. And you can find the code for this algorithm in our GitHub repo. So we run our attack on some known database. So for example, we get a nationwide inpatient sample from a healthcare cost and utilization project. we select 10,000 records from that database, and we perform range query on the A months column, which has 12 attributes. We run different scenarios. One is real database, the other one is synthetic database. Also, we look at uniform query and also non-uniform query. As you recall, the uniform is what the case where the previous work considered. We also consider non-uniform query. And also, we look at the case where there is no extra load or where there is noisy process running, and an interesting case where the large volumes are dropped. So for example, if you ask for the whole database, or if you ask for a range 1n, the biggest range possible, that will be dropped by database. We look at the cases where that happen, if we can recover the database. So the figure on the left-hand side shows the variation of the attack when the noise parameter is increased. You can see that as we increase the noise parameter, we could recover more and more elements of the database. But even with the 0.06, 0.006, we could not still recover the whole database. But by using match and extend, we can almost recover all the elements in the database. And also, we look at the error rate in the elements that we recovered, and we find that match and extend performed better than increasing the noise parameter. Also, for the case that the large volumes are dropped, we show that even if you drop anything above 70%, we can recover 98% of the elements. So for more results, please refer to the paper. Thank you for listening. If you have any question, please let me know. Thank you.